Okay, in this section, we're going to look at curve sketching, and we're going to use the techniques we've looked at, and together with some of your previous skills from your pre-calculus classes. There's these 7 steps we're going to follow. So this is what they mean when they say the guidelines in the book. Here we go. Let's just get into it. So when you give a function, now, oh, by the way, I would suggest what you do is download the blank handout here. It's in the other answer keys and handouts module, okay? So do that first and see if you can do this on your own. How about this? Now, we're going to look at more complicated functions, not polynomial functions. They're pretty simple. Let's look at ones where it's a little harder. All right, this is a rational function. What is the domain? The domain would be all real numbers, correct? Because the bottom's never 0. The intercepts, the x and y intercepts. The y-intercept is f of 0, which is 0, and the x-intercept is also 0. Symmetry. Now, is it even, odd, neither? Is it periodic? You'll notice that f of negative x equals negative f of x. I should have said that f of negative x equals negative f of x. Therefore, it's odd, right? Good. Horizontal asymptotes y equals 0 because the denominator has bigger degree than the numerator. All right, here we go. So when is it increasing? It's increasing when the derivative is positive. So I'm going to go quickly over this. With some of these, the hardest part is finding f prime and f double prime, isn't it? Anyway, the derivative of this function should be 4 minus x squared. It equals 0 when x equals plus or minus 2. Now, you should also look where the bottom is 0 because a function can go from increasing to decreasing where f prime is undefined. In this case, the denominator is never 0, so we don't have to worry about it. But you should also consider places where f prime is undefined because the function can go from increasing to decreasing at a vertical asymptote. Oh, so, okay, so when we use the first derivative test on this, we plot 2 and negative 2, and you find that f prime is negative to the left of negative 2, and also greater than 2, and f prime is positive between negative 2 and 2. So that means that there's a local min at negative 2 and a local max at 2 by the first derivative test. Concavity, well, again, the derivative can be kind of a mess. I just did this for you. The derivative of this, check me if I'm right. What's the derivative of this function? I get this. I factored it. There's quite a few steps I just skipped there. The derivative is 0. Oh, by the way, this should be x squared plus 4, right? The derivative is 0 whenever x equals 0 or 2 plus or minus 2 squared root of 3. So when you look at this, when x is less than negative radical 2 squared root of 3, this one's negative, but this one's positive. And when x is between negative 2 square root of 3 and 1, let's just pick negative 1. When you pick negative 1 in, this is negative and this is negative, so it's positive and so on. So it's going to be concave up here and here, concave down here and here, and you have inflection points, right? These are places where f double prime changes sign, and they have to be in the domain of the function. And the domain of the function, remember, is all real numbers. Okay, so last thing we're going to do is look at the graph. I know on a quiz you could always look at the graph first, but it's nice to justify what the graph shows you. The graph of this function, you have a local max. The local max was at 2, local min at negative 2. That looks about right here and here. And then the inflection points, you've got 3 of them, right? You have an inflection point at 0, and inflection points at plus or minus 2 squared root of 3. Hit the pause button. Find the domain, the intercepts, the symmetry, the asymptotes, the intervals where f is increasing and decreasing, and the intervals where it's concave up and down. Okay, let's go over this. I'm going to go pretty quick here. Let's see. The domain x cannot equal 4, right? X cannot equal 4. The intercepts, f of 0 is 0, and the x-intercept is 0, 2. No symmetry. It's not even, it's not odd. There's a vertical asymptote at 4. By the way, since the top has degree 1 more than the bottom, they didn't ask you for this, but there is a linear asymptote, right? Linear asymptote, you would divide and you get the linear asymptote as y equals x plus 4. Did you get this for f prime? X times x minus 8 over x minus 4 squared. And so you plot the places where the derivative is 0. Now, undefined at 4, you have to include that on your sign chart because, like I said, the function can go from increasing to decreasing at a vertical asymptote. Don't forget to do that. Even though it can't be a local maximum in there, but the function can still go from increasing to decreasing. This one doesn't, but it could. Anyway, so this is what I get from my sign chart. So there's a local max at 0, local min at 8, and there is no sign change at the vertical asymptote. It's decreasing to the left and to the right. For the second derivative, it's kind of a mess. When all the dust settles, I got that. And so it's going to be, now the only place, it's never 0, but notice the concavity could change at the vertical asymptote. And it does, actually, because if x is less than 0, the second derivative is negative. If x is greater than 0, the second derivative is positive. So at the vertical asymptote, the concavity changes. We wouldn't call that we wouldn't call that an inflection point, though, because it's not in the domain of the function. So you see you have your local max here, your local min here, and you have the concavity changes. Concave down here, concave up here. Amazing, isn't it? This one is this to the 1/3, x squared plus 9 to the 1/3. So what is the domain? The domain is all real numbers, right? You can have a cube root of a negative number. The intercepts, if you plug in 0, you get the cube root of -9, which is defined. And the x-intercepts, you plug, it's at plus or minus 3, right? Plus or minus 3. Anyway, okay, so we got that. And then the symmetry, it turns out it's even. It's not too hard to see that. If you plug in negative x, you show that f of negative x is f of x, so therefore it's even. Asymptotes, there's no vertical asymptotes. Now, when you take the derivative, again, I'm going to go quickly over that part, because that's the messy part. The derivative, we're going to look at places where, no, this is important. At 0, it's a critical number. By the way, 3 plus or minus 3 is a critical number because it's where the derivative is undefined. But notice it's in the domain of the function, so it's not a vertical asymptote. 3 and negative 3 are critical numbers, and so it turns out you have you don't have any sign change at negative 3 or 3. The only sign change is at 0. So you have a local min. Is that right? Local min at x equals 0. Now, for the second derivative, again, it's kind of a mess. I got this. It took me a while, but I got this for my second derivative. Again, you have to look at the only places where it's 0. It's never 0, right? Because this is never 0. But there are places where f double prime is 0. Now, those are potential inflection points because plus or minus 3 is in the domain of the function, right? So they are perfectly good candidates for inflection points. In fact, the concavity does change at plus or minus 3. So the graph looks kind of like, find the domain, find the intercepts, find the symmetry, find the asymptotes, especially the intervals where f is f prime, where the f is increasing and decreasing, and f is concave up and down. So I'll hit the pause button, try that one, and we'll go over it. Okay, this one really isn't that bad. Its domain is all real numbers. The only place where this is 0 is when x is 0. What's a y-intercept and an x-intercept. No symmetry, it's not periodic. It turns out it's kind of like periodic, but this is not going to make it periodic because it doesn't repeat. No asymptotes. The derivative is pretty easy. The derivative becomes 1 plus cosine of x. Notice, it's 0 whenever x equals 3 pi over 2 plus 2n pi, but it's never negative. You look at it closely. This is never negative. It's always positive, or it could equal 0. So what does that say? The function is always going to be increasing, except where f prime equals 0. So there are no local max or min. And then this one, the second derivative is negative sine x. The places where that's 0 is at n pi. And if you make a sign chart here, what you realize is you have local max at 0 and a local max, wait a second, we're talking about concavity. It's concave up from pi to 2 pi and from 3 pi to 4 pi. So how would you write that down? It's like if it starts on an odd pi and then goes to an even, you could say all possible 2n plus 1 pi's to 2n plus 2 pi's, where n can be any integer. So this would take care of all the places where it's concave up. All the places where it's concave down, it would be all the even pi's, and then the next one over would be an odd pi. So that's how you could write it, like that. All right, so the graph looks kind of like this. Interesting, huh? Kind of like a piece of some kind of lasagna noodle or something like that. I don't know. All right, we'll talk to you later. Bye-bye.